let us find minimum and maximum of the function x plus y plus 2, okay, on the curve x squared plus 2y squared is 1. Okay, as we will see quite soon, the geometry is quite simple, but we will, of course, use Lagrange's method. Now, first of all functions are differentiable, so we have no problem there. They are polynomials, and so on. And because this is the constraint, and our hxy will be 0, so it is x squared plus 2y squared minus 1. Okay, that will be 0. So this is my h. The constant is not important here because we will be dealing with the derivatives at first. However, the point will satisfy this equation as well. So let us construct the Lagrange. Okay, we have gradient f plus lambda gradient h is 0, 0, and h of p, or let me say p0, so everything happens at p0, this will be 0. So this is what we have. What are these? Of course, okay, if we look at the first components, this is f sub x plus lambda h sub x. Well, f sub x is 1, plus h sub x is 2x, but we have a lambda there in front, and that will be 0. The second one, again, the derivative with respect to y is 1, and here we have 4 lambda y, that will be 0, and h is 0, so x squared plus 2y squared is 1. So we have 3 equations. Okay. We want to solve them. Well, before we attempt a solution, we first observe that x, y, or lambda cannot be 0. Because if any one of them is 0, from 1 and 2, we get a contradiction. So the first observation, x, y, or lambda is not 0. Otherwise, we get contradiction 2, 1, or 2. Okay, why do we need such observations? Well, 0 is important here because sometimes we will be dividing by these numbers. Of course, we can try a direct substitution method. Okay, so we can solve for lambda as minus 1 over 2x from 1. Put in 2. And then there will be an equation without lambda, and you can solve the 2 resulting equations. And solve for xy using equation 3. Okay, this is substitution. Which, as we already know, is not a very good idea all the time. Well, here, of course, you can, if you do that, what do you get, by the way? If you put 1 over x, yes, it is possible here. It's not a bad idea, a very bad idea, but easier is the following, as we already observed. Okay, subtract or do something and obtain products equal to 0. Well, from here, for instance, we easily see that 1 minus 2 gives, okay, 1's cancel out, so we have 2 lambda, okay, and then x minus 2y is 0. That's right, we subtract, so we get this. Well, that says we have two possibilities. Lambda is 0 or x is 2y. But we already said that lambda cannot be 0 because it contradicts, say, 1. 1 is not 0, so it's not possible. Well, x is 2y. Well, we can put it in 3. And this gives us x squared, that is 4y squared, plus 2y squared is 1. Okay. So we get y from here as root of 1 over 6. Okay. So P1, okay, well, x is 2y, so it is 2 over root 6 and 1 over root 6. Okay. And P2, which is the negatives, so it is minus 2 over root 6 and minus 1 over root 6. So we get 2 points from here. There is nothing left that we did not analyze. Now we put them in F. So F of P1, okay, our F was x plus y plus 2, so you just add them. For P1, it's 3 over root 6 plus 2. For P2, it is minus 3 over root 6 plus 2. Of course, this is the maximum. This is the limit. Okay, why? Well, because the curve in question at the bottom is an ellipse. Okay. Namely, okay, why are we sure that this is maximum and this is minimum? We only know they are critical points. Okay. But we know also the following. The function f is continuous on the closed and bounded curve, which is the ellipse. So there is a maximum and there is a minimum value in the first place. And they are critical points, and we have 2 of them. So that's it. So we are finished. On top of the ellipse exists. Well, these points are solved so that they are actually picked up from the ellipse, and so everything is fine there. Okay. What does the geometry look like? Well, F is a plane in the first place. The other one is an ellipse. So the geometry looks like the following. Okay. At the bottom, we have an ellipse, namely x squared plus 2y squared is 1. At the top, we have x plus y plus 2, a plane. So what curve are we investigating? We are looking at the curve at the top, perhaps something like this. Now, clearly, there is a largest and a smallest value, which occur at, okay, opposite sides in some sense. And of course, this tells us exactly that. So this is the minimum value. This is the maximum value. And we expect two of them because the geometry tells us exactly that. Okay, let us now apply this method to a distance problem. Namely, let us find the distance. Okay, of course, the shortest all the time. It could be, in this example, the largest as well. From x squared plus y squared plus z squared is 1 to the point. By the way, this is a sphere, of course, to the point, say, 1, 1, 3. Well, we considered such shortest distances between planes and points, okay? But here we don't have a plane. We have a surface, okay? So the derivative must be used. But what is the question actually? Okay, the question is the following. Is to find, okay, minimum of, okay, the distance between P0 and P on the sphere as a function of P. What is this distance if we call this x, y, z, and this x0, y0, we know what P0 is. So this is actually the first component up to x squared, y minus 1 squared, plus z minus 3 squared under the root. Okay. So we want to minimize this function, which has 3 variables, by the way. But the point x, y, z is chosen from the sphere. So, and we have x squared, y squared, z squared is 1. Okay. So we have okay, a restriction here, the constraint. So this is a Lagrange problem. Okay. But we have 3 variables. Okay. Now, with respect to distances, let me note the following. Okay. Since for x positive, okay, x squared is increasing, okay, minimum occurs, okay, let me see, yes, minimum of distance occurs exactly at the same point as the minimum of distance squared occurs. Okay, you should think about this a little bit and make sense of this statement. What I'm saying is, instead of considering the square root, I can forget it. Okay, so consider instead the distance between P0 and P squared. That's simply x minus 1 squared, y minus 1 squared, z minus 3 squared. Okay. And, of course, you can call this your function now. And, of course, the other constraint, this is a point on the sphere. So we construct, okay, so applying Lagrange, okay, we have gradient f, that's the gradient of this f, and of course this will be my h plus lambda gradient h is 0, 0, 0, and h of P0, everything at P0, so I will not use, well, P0 is a bad idea. So let me say at P will be 0. Okay. So what do we have? We have actually 3 equations coming from here and another from here. So it's 4 equations. And 4 unknowns. X, Y, Z, and lambda. So this is a Lagrange problem. What does all that say? Well, gradient f is the derivatives. So the first component is twice x minus 1 plus lambda, the derivative with respect to x of h, which is 2x, that should be 0. Secondly, twice y minus 1 plus, okay, lambda 2y will be 0, and twice z minus 3, derivative with respect to z, plus lambda 2z will be 0. And the last equation, x squared y squared z squared is 1. Okay. Now what can we do about these things? Well, we can formulate this a little bit in a better formulation. Say we put x's together. So we have x times 2 plus 2 lambda minus 2 is 0. Y times, well, 2 plus 2 lambda minus 2 is 0. And finally, here, we have z, okay, 2 plus 2 lambda, and minus 6 is 0. Let me call these the equations 1, 2, 3. And this 4, of course. Okay. Now, the first observation, if one of x, y, or z is 0, okay, we get a contradiction. Okay. Namely, if x, y, or z is 0, we have minus 2 equal to 0, or minus 6 is equal to 0. So if x, y, or z, not all of them, but if one of them is 0, okay, then we get contradiction 2, 1, 2, or 3. So first of all, they are not zeros in the first place. Well, secondly, okay, consider the subtraction 1 minus 2. What does it tell us? Minus 2's cancel out. We have x minus y, and 2, of course, and 1 plus lambda is 0. Well, when we look at this formulation, we have two things, x is y, or lambda is minus 1. But lambda cannot be minus 1. Just consider the first equation. Okay? If lambda is minus 1, you will have minus 2 equal to 0. So this contradicts, okay, 1, for instance. Also 2, but we don't care. Also 3, so we don't care about that. It cannot happen. Well, if x is equal to y, what happens? If x is equal to y, the two equations are the same. Okay? And we can, of course, what do we get from there? If x is equal to y, okay, let us look at 2 minus 3 type of thing, okay, so that we eliminate lambdas here. Okay. However, we cannot do that. We have to multiply the second one by 3. So here, consider 3 times, okay, the second equation, say, and subtract from it the third one. We get, okay, I want to eliminate the constants. Okay, so we get y times 2 plus 2 lambda. And here, because we multiplied this by 3, okay, and we have minus 6, but they cancel out. And from this, we subtracted z times 2 plus 2 lambda. And that should be 0. Okay, because minus 6 canceled, and we get this. Well, this tells us, of course, that 2 times 1 plus lambda and 3y minus z must be 0. We know this is not 0 because lambda cannot be minus 1. We already considered that. We get a contradiction. So it says that z is 3y. Well, we have all the equations we want. Put them in 4. So put in 4, okay, x equal to y, because in this branch, we are in this branch still. We are in this branch. X is equal to y. And so the other one gave nothing. So I wrote this in the wrong place. I should write it here. 3 times 2 minus 3. Because this gives contradiction, there is nothing more to it. Okay, and also z is 3y. So in 4, this means that you square them. So you have y squared, that's x squared, plus y squared, plus 9y squared is 1. So y becomes 1 over 11 under root plus minus. So what are the points? Okay, x is equal to y, so it is 1 over root 11, 1 over root 11, and z is 3 times y, so it is 3 over root 11. And for P2, we take the negative root, minus 1 over root 11, minus 1 over root 11, and 3 over root 11 under the minus sign. Now, when you put them in place, okay, that is in the function x minus 1 squared, etc., etc., you see that one of them gives the maximum, one of them gives the minimum. So put in f x y z. Okay. So one of them is maximum, other. Again, the minimum and maximum exist in this case, but we can even see it from the geometry. Okay. Because what we are, of course, saying is the following picture. Okay, we have a sphere and we have a point. Clearly, this point is not on the sphere. You can easily check that. So, okay, if you draw a perpendicular to this surface from here, you will find one point, and if you continue, you will find another point. One of them is P1, the other one is P2. Okay. So one gives the biggest distance, the other gives the shortest distance. You just have to try them in place. Okay. Well, let us consider now a different example. Question is, find the minimum and maximum of f x, y, z, which is xy plus yz, okay, subject to the constraints x squared plus y squared is 2, and yz is 2. Okay. Of course, this fits to the standard problem in the first generalization. That is, okay, the intersection of these two curves, these two surfaces is a curve. We are looking for the maximum minimum of this function on top of this curve. Okay. So what do we have here? Well, this is a Lagrange problem. Okay. So here, call this, say, G or H. Okay. Say H x, y, z is yz minus 2. Say G O x, y, z is x squared, y squared minus 2. Okay. So then we construct gradient f plus lambda gradient g plus mu gradient h is 0, 0, 0. And the equations must be satisfied. X squared plus y squared is 2, and yz is 2. Okay, what does all this say, by the way? Let us evaluate the derivatives. The derivative of f with respect to x would be just y. And the derivative of g with respect to x would be 2x. The derivative of h would be 0. So that would be 0 with respect to x all. And with respect to y, okay, the first one would give us x plus z. The second one would give us 2y. And h with respect to z would give us y. Oh, sorry, z. And that would be 0. And with respect to z, the first one gives y plus, okay, lambda times 0, because we have no z in the second one. And finally, in the last one, we have y. So this is 0. Okay, well, let me just check if I did that correct, because I don't want to mess it up. So we have all that, right? And we have this one, all right. And we have, yes, of course. When we evaluate this with respect to z, this would be y. Okay. You can call these the equations 1, 2, 3. The last two, and yz equal to 2, can be called 4 and 5. Clearly, we have 5 unknowns and five equations, and we want to solve the system. And of course, some of them are not linear systems, not linear equations. Okay, but we observe a few things. For example, from 3, okay, we get mu plus 1 times y is 0. Okay. Now, if y is 0, okay, we have, what do we get if y is 0? Let me see. If y is 0, we have, of course, the fifth equation contradicted. So, this contradicts phi. So it's out of the question. So mu must be minus 1. What happens if mu is minus 1? Well, from the first equation, we have nothing new. Y is, okay, y plus 2 lambda x is 0. So it is the equation itself. From the second one, minus z cancels with this one. So from 2, we get x plus 2 lambda y is 0. Okay. And if mu is minus 1, the last equation is satisfied. That's where we started. So we don't get anything new from there. Okay. Now, if x or y is 0, let us observe here that if x is 0, for example, okay, now one says that okay, y must be 0. Okay. Then by 1, y is 0. Okay. Or from here, okay, y is 0. So these two equations are satisfied, but y cannot be 0 because y times z is 2. This contradicts 5. So x cannot be 0. Okay, and clearly y is not 0. Okay, because of this condition. So it says that x and y cannot be 0. Okay. If they are not 0, then okay, we can multiply these equations by these constants. Why do we want to do that? Because we want to cancel them out. Okay. We want to cancel lambdas out because we don't want to find lambda. Okay. So multiply 1 by y, 2 by x, okay, to get symmetry. Okay, why do we want, okay, the factors x or y to be non-zero? Well, because of the following. If you have an equation, and if you multiply both sides by a 0 value, what remains? Nothing remains. 0 is equal to 0. So to have the information still so that it will not go away, it will not disappear, you want your factors to be non-zero. So we need it, that is to say, we need x, y different from 0 so that we don't lose information. When we multiply. And we know that. We know that they are not 0. So, okay, what happens? Multiply this with y. So y square plus 2 lambda x squared, sorry, by y, so this is y, is 0. And in the second one, we multiply it by x, so it is x squared plus 2 lambda xy is 0. Subtract. Okay. Y equal to x, or y equal to minus x. Now, this information is enough for our purposes. Okay? We are not concerned about mu or lambda, so we will not go back to the first 3 equations, but the last 2 ones. So now, okay, so if y is x, then by 4, okay, well, what was 4? 4 was, well, I did not name it, but 4 is the cylinder, x squared plus y squared equal to 4, is 2, okay? We get, okay, 2x squared is 2, so x is plus minus 1, okay? And of course, it means that we get a point 1, but y is equal to x, and by 3, or by 5, that means now yz is 2. Okay? If y is 1, z must be 2. For P2, if x is minus 1, y is equal to it. And by this equation, that must be minus 2 similarly. Now, if y is minus x, we get, okay, I will not explain this, just the same way, we get, again, x is, or y is plus minus 1, but now they are oppositely signed, so we get P3. If x is 1, y must be minus 1, so z must be minus 2, and finally, minus 1, 1, because y is 1, z is 2. So we get 4 points. Okay. Now, what do these tell us? Well, our function was xy plus yz. Okay. We get f of p1. Well, x and y are minus 1s, y is negative, so it's 1 plus 2, it's 3. But this is the same, okay, for p2. And f of p3, that is, they are oppositely signed now, would give us minus 1. And, right, that's xy. And yz would be 2, so this would be 1. But that's the same as p4. So, okay, this is the minimum. This is the maximum value. They occur at 2 points. Okay. Well, last comment here. Since yz is 2 is a constraint, we could look at fxyz, xy plus yz, but this must be 2, so it's xy plus 2 directly. This would have simplified the calculation a little bit, but not too much. Okay. Well, by the way, are we sure that there's a minimum and there's a maximum value? Well, yes, because the constraint x squared plus y squared is 2 says that x and y must be bounded from below and from above, okay? And the last one, yz is 2, says that if y is bounded, z cannot be too large. Okay. Right, can y be 0, for example? Okay. Well, we check that it's not possible because we get a contradiction from the conditions. Okay. Right, now we continue with our fourth example. Okay. Now, in this problem, you can, of course, use direct substitution and use the methods of one variable case, but this is not what we want to do here. This is a Lagrange problem, okay? Clearly, everything is a polynomial, etc. So here, this is the constraint. I will assume it is x cubed y cubed minus 1. And so we construct gradient f plus lambda gradient h is 0, 0. This means, of course, y, and the derivative with respect to y would be x, okay, and plus lambda 3x squared and 3y squared. That should be 0, 0. Okay. So y plus 3 lambda x squared is 0. X plus 3 lambda y squared is 0. And finally, of course, this must be satisfied. The sum of the cubes is 1. So call this the first equation, the second, and the third equation. Now, of course, the idea is to make lambdas go away. Okay. The first thing to start with is that if x is 0, okay, by 1, y is 0. Well, 3 says that the sum of the cubes must be 1, and it cannot be satisfied in this case, so contradicts 3. Now, similarly, y cannot be 0. Because this time from 2, if y is 0, x must be 0, so contradicts 3. So these must be non-zero values in the first place. Okay. If they are non-zero, then we can form the equations so that we can cancel lambdas. That's to say, I will multiply the first one with y squared, the last one with x squared. So form the following, okay? Y squared times 1 minus x squared times the equation 2. Now, what does this give us? If you multiply the first one with y squared, you get y cubed plus 3 lambda x squared y squared. Okay. But when you multiply the second one with x squared, you get x cubed plus the same thing. Subtracting, they cancel out. So we get this. Well, this means that y is x. Well, if y is x, the third one says that we get the point. If they are equal, you have 2x cubed, so 1 over cube root of 2. Okay. And y is equal to it, so it is 1 over cube root of 2. So we have only one critical point. Is this a minimum or a maximum? Okay, rather, does this give Now, this is a serious question, of course, because we got only one critical point, and we are not sure if it gives us minimum or maximum value. Okay. So one of them possibly does not exist. So a better question is, do the minimum and maximum values exist? Now, when we look at the problem directly, okay, we have x cubed and y cubed. Well, what does this mean, by the way? Of course, if we can find values, that is points, satisfying the constraint, and putting in F, can we get values going to infinity, going to minus infinity? Namely, if we can find such values which make the function go to infinity, it will say that the function does not have a maximum. So if so, maximum does not exist. And here, if so, minimum does not exist. So let us investigate this directly. Okay. Well, a nice value which will make the function go to infinity, for instance, could be a trial using positive integers. So, say, okay, x is an arbitrary number in n. Then, okay, by constraint, choose y, okay, but it must satisfy that the sum of the cubes is 1, so it will be 1 minus the cube under the cube root. Then, of course, the sum of the cubes will be 1, so it will be a point from x cubed plus y cubed equal to 1. Now, put in f. Okay. Well, f was just xy, so f of n and 1 minus n cubed, cube root is just n times 1 minus n cubed, cube root. Of course, if n is larger and larger, this part will go to minus infinity because the cube is an odd function. You can take minuses out. Multiplied by n gives you minus infinity when n goes to infinity. This means that there is no minimum. Well, is there a maximum? Well, to make xy maximum, x and y must give us values so that the product is positive. Okay? So, okay, should be okay, with same sign. Well, this can happen in two ways. Namely, if x and y are negative, same sign, then of course x cubed plus y cubed equal to 1 is violated. So it's not possible. You don't have any points xy, both negative, satisfying this equation. Okay. So xy, okay, must be positive or 0. Well, in this case, that x is between 1 and 0, y is between 1 and 0, and so xy cannot go to infinity. Okay, so there is a maximum. Okay. Conclusion. Okay. The point in question, that is P0, gives the maximum under the conditions. The minimum is minus infinity. Okay. Now, this analysis, or rather the importance of this analysis will be clearer if we consider a three-dimensional version of this problem. Okay, namely the following. Say 4 prime, find minimum, maximum of x, y, z subject to x plus y plus z is 1. Okay. Now, being a Lagrange problem, I will not go into more details, directly start calculations. Now, the gradient of f is just yz, xz, and xy. The gradient of h, call this H. Okay. This would be 1, 1, 1. Okay. So, the equations we get, yz plus lambda times 1 is 0. Xz plus lambda times 1 is 0. And xy plus lambda times 1 is 0. And the sum is 1. So this is the first equation. This is the second and third and fourth. Okay, we want to cancel things. But it's obvious if you just subtract 2 from 1, okay, you get yz minus xz. So you get this. You have two possibilities. Z is 0 or yz. Okay. Well, if z is 0, clearly lambda must be 0 from 1. And this says that, because lambda is 0 now, from 3 we have xy is 0. There are two possibilities, x is 0 or y is 0. Now, if x is 0, okay, z was 0 already. If x is 0, the fourth equation says that z is 1 by 4. And if y is 0, this means x is 1, again, by 4. Okay. That's fine. Now, if y is x, what happens? Well, if y is x, 1 and 2 become equivalent. So they don't give us any new information, okay? But we can consider 2 minus 3 now. Now, 2 minus 3 gives lambdas go out, okay? You have x times z minus 1 is 0, which says x is 0 or z is 1. If x is 0, then y is 0. So 4 gives z is 1. If y is z and y is x, this gives, again by 4, that x equal to y equal to z equal to 1 over 3. So all in all, what do we get? Let us consider these cases. Okay. From this branch, we had z0 and x0. So we start with y1. This is one of the points that we get from here. And from this side, z is 0 and x is 1 and y is 0. So we get x is 1, the others 0. Okay. This is from the left branch. From the right branch, okay, we have y equal to x and z is 1. Well, if z is 1 and y equal to x, okay, 4 says that you have 0, 0, 1. And finally, the last one, that's to say 1 over 3, 1 over 3, 1 over 3, from right branch. So we have 4 points. Okay. Now, if we look at the function, which is x, y, z, we get 0 or 1 over 3 cubed from these points. So, is this the minimum and is this the maximum value? Well, the answer is quite strange. The answer to both ways, minimum or maximum, is no. Because there is no maximum, there is no minimum in this case. Because of the following. Okay, the constraint is that the sum will be 1. So take n plus n, and plus 1 minus 2n. This is x, this is y, this is z, sum is 1. But of course, x, y, z is n times 1 minus 2n, which goes to minus infinity, so no minimum. You can pick up points satisfying the equation, but they make the function value go to minus infinity, so there can be no minimum value. Also, take, for example, minus n, and 1 plus 2n. Well, this is again 1. This is your x, this is your y, this is your z. The sum, of course, is 1, and x, y, z function will give you minus n, and 1 plus 2n, which of course goes to infinity, so no maximum. So what are the 4 points we found then? Well, they are critical points. Okay, a critical point need not be local maximum or local minimum. It can be any strange thing, only the tangent line is horizontal. That's all we know. So, in this case, then, it is necessary to check if they exist or not. Because just by finding 4 points, you cannot conclude anything, because these don't exist. Okay. A final version, which I will demonstrate now, will be the thing that the following. Now, of course, these problems, that is, no maximum, no minimum, occurred because we could take negative values. Now, if we take no negative values, if we assume x, y, z are non-negative, okay, namely, this will be a new version, okay, same as 4 prime, but x, y, z are positive. So what is the situation in this case? Well, in this case, actually, what is happening is that we have 3 points satisfying, okay, the equation of a plane. And they are positive. So, the point x, y, z is taken on the plane okay, their sum will be 1. Okay, these are all 1s. So this is the restriction. We choose our points on this plane, but in the first quadrant. Okay, we don't go to negative values. x, y, and z are all non-negative, so we choose them from here. Well, obviously, because they are non-negative, if one of them is negative, the product is 0. And you cannot get a negative value by multiplying 3 non-negative values, which means that 0 is the minimum value. So, clearly, okay, if 1 over x, y, z is equal to 0, then x, y, z is 0 gives minimum value. Because you cannot get a negative value anymore. And this indeed occurs because okay, if you choose a point from this triangle, okay, whether you are on the sides, it doesn't matter which one of the components will be 0. So, okay, this happens on the edges. Well, this means sides in geometry of the triangle. So, for all points on the perimeter of this triangle, we get the product 0. Okay. Do we have a maximum? Well, of course we do. Because in this case now, okay, this triangle is closed and bounded. There is a maximum and a minimum. Okay. And of course, x, y, z is okay, f x, y. Correctly. Is continuous. It has minimum and maximum. So, okay, the other critical point, 1 over 3, 1 over 3, 1 over 3 gives the maximum.